Some nights the sky holds a kind of stillness that feels almost deliberate, as if the darkness itself has settled in unhurried and decided to stay a while. If this feels like a good place to rest tonight, you are welcome to stay. Now, let's drift. There is something quietly extraordinary about the universe that most of us carry through our days without ever really stopping to feel. Not a fact exactly, more like a texture. A sense that for all the brightness we can name every star we have ever mapped, every galaxy photographed, every particle measured in a laboratory, there is something else. Something vast and patient and entirely invisible surrounding it all, threading through it all, making up most of everything that has ever existed. And we have not found it yet. Think for a moment about what we mean when we say we know the universe. We mean the light. We mean everything that emits or reflects or absorbs radiation in some form we can detect. Radio waves arriving at enormous dishes on quiet hillsides. Infrared light revealing the warmth of distant gas clouds. The faint blue shimmer of galaxies billions of light years away, captured in a photograph that required weeks of stillness from a telescope drifting high above the atmosphere. It is remarkable, all of it. Genuinely remarkable. Over centuries, human beings built instruments of increasing delicacy and patience and turned them outward, and the universe answered back with more than anyone had imagined. But here is the quiet thing that researchers have come to understand, and it arrived not with drama, but with a kind of slow, careful arithmetic that took decades to absorb fully. Everything we have ever detected, everything that has ever registered on any instrument ever built, everything that emits light or responds to light in any way, all of it, every star, every planet, every cloud of hydrogen drifting between galaxies, every black hole pulling matter inward, every nebula glowing in wavelengths too long or too short for human eyes to catch all of that visible, measurable, detectable universe adds up to somewhere around 5% of what actually exists. 5%. Scientists suggest the remaining 95% is composed of two things we cannot directly observe, cannot sample, cannot touch, and have never in any laboratory on Earth successfully captured even a single particle of. One of those things holds the universe together, the other pushes it apart, and both of them are everywhere. It's worth sitting with that for a moment the way you might sit with something unexpectedly large, not rushing to explain it or resolve it, simply allowing it to be as large as it is. The universe, as best as researchers have been able to determine, is mostly made of something else, something other than what we are made of, other than what everything we have ever seen or touched is made of. The atoms in your body, the air moving gently in and out of your lungs right now, the mattress beneath you, the walls of the room, the earth itself. All of that is part of the same visible 5%, the ordinary matter that responds to light, the matter that can be detected. The rest moves through all of it without leaving a trace. This is not a gap in knowledge that will be filled next year or the year after. It is a deep and genuinely open question, one that the most sophisticated physics of the last century has not resolved. The standard model of particle physics, which describes the fundamental building blocks of matter with extraordinary precision, does not include an explanation for what makes up most of the universe. The equations that govern the behavior of light and electrons and quarks, and the four known forces equations that have been confirmed to an almost absurd degree of accuracy in particle accelerators and laboratories around the world, those equations have nothing to say about what fills most of the cosmos. It may be that the universe is simply larger in some fundamental sense than the tools we currently have for understanding it. The story of how we came to know this, how scientists gradually, carefully, and in some cases reluctantly concluded that most of what exists is invisible, is one of the quieter detective stories in the history of science. It did not involve a single dramatic discovery. It accumulated over decades through the work of astronomers and physicists who are often looking for something else entirely and kept finding something they did not expect. In the early 20th century, a Swiss astronomer named Fritz Zwicky was studying a collection of galaxies known as the Coma Cluster, a dense gathering of hundreds of galaxies moving together through space. He measured how fast the individual galaxies within the cluster were moving relative to one another, and when he compared those speeds to the amount of visible matter, the cluster contained all the stars, all the gas, everything that could be detected. He found that the galaxies were moving far too fast. The visible matter was not nearly heavy enough to produce the gravitational pull needed to hold the cluster together at those speeds. The galaxies should have scattered outward long ago. Zwicky proposed that there must be additional matter that couldn't be seen. He called it, in the German of his original paper Dunkle Materie, dark matter. For decades, most of the scientific community set the idea aside. It felt too strange, too convenient, a kind of invisible answer to an awkward problem. And the data was limited. One unusual cluster, perhaps a measurement error, perhaps a misunderstanding of how gravity behaved at large scales. But the idea did not disappear. It is interesting, researchers have noted how often the universe turns out to be stranger than our first instinct assumes. The history of astronomy in particular is a quiet series of revisions, each one expanding the picture outward or inward, each one revealing a layer that was not expected. The Earth moved from the center of the cosmos to a planet orbiting an ordinary star. That star turned out to be one of several 100 billion in a single galaxy. That galaxy turned out to be one of somewhere around 2 trillion in the observable universe alone, and each time the picture expanded there was a period of adjustment. A moment when the new information had to settle into the existing framework, and the framework had to stretch a little to accommodate it. What scientists gradually came to understand about the invisible universe over the second half of the 20th century was another such adjustment, larger perhaps than any that came before it. Because it was not simply adding more of the same kind of thing, it was suggesting that the same kind of thing, visible matter, ordinary atoms, was the exception rather than the rule. The universe is mostly dark, not dark in a threatening sense, but dark in the way a deep and quiet room is dark. Full, still, present. There is something that happens, some people find, when a piece of scientific understanding settles into a feeling rather than just a thought. When a fact about the cosmos stops being an abstraction and becomes for a moment something almost physical, something that changes the texture of the air in the room just slightly. It may be that the invisible components of the universe are everywhere around you, right now, tonight, as you lie still. Not waiting, not doing anything exactly, simply present in the way that very large and very old things are present, without urgency, without announcement, without any need to be noticed. The body does not feel them. No instrument on Earth has directly detected them, and yet every galaxy in the universe, including the one you are a small and luminous part of, appears to be held in place by something that has never once been directly observed. Researchers are still working to understand it patiently, carefully, with the quiet attentiveness that this kind of question seems to require. Different teams working in different countries with different instruments and different theoretical frameworks, all circling the same enormous and beautiful uncertainty. What is most of the universe made of? The answer for now is we don't fully know, and that is not a failure. That is exactly where science lives when it is doing its most important work at the edge of what can be measured, looking carefully at what cannot. For tonight, there is no need to resolve it. The universe has been quietly keeping this particular arrangement for something close to 14 billion years, and it shows no sign of becoming any less mysterious before morning. The dark components were there before the first star ignited. They were there when the earliest atoms formed from the cooling remnants of the beginning. They will be there long after every star in our and every galaxy has spent its last reserves of hydrogen and quietly dimmed. They have time, and in that sense perhaps there is something almost restful in what researchers have found, not despite the mystery but because of it. The universe is not fully legible. It does not hold all of itself to being known. It holds something back distributed quietly through every corner of space, and it does not seem to mind that we have been searching. The night, after all, has always held more than the eye can find in it, and in the particular silence of the cosmos behind the visible light behind the stars and their ancient warmth, something else is there. Something that holds everything in place without ever once being seen. Something that some scientists are beginning to suggest may be more fundamental to the structure of everything than the matter we have spent centuries studying. We will follow it softly from here into what the universe has been quietly holding all along. There is a particular quality to starlight that is easy to overlook, not its brightness or its colour, or even the distance it has travelled, but the fact that it is information. Every photon arriving from a distant star carries a small faithful record of what that star is made of, how hot it burns, whether it is moving toward us or gently away. For well over a century, astronomers have been reading these records with increasing care, building piece by piece a picture of what the visible universe contains. And what they found was extraordinary, not 2 or 3 galaxies, not a few thousand, but something closer to 2 trillion. Each one a vast collection of stars, gas dust, and older light, all held together by gravity, all moving in their slow and ancient patterns through the dark. 2 trillion, a number so large it has no real shape in the mind. It simply sits there quietly, the way very large things sometimes do. For a long time this felt like the whole answer. Researchers had mapped the distribution of galaxies across enormous stretches of space, had calculated the mass of clusters, and superclusters had traced the large-scale structure of the cosmos into something resembling a kind of foam. Vast empty voids surrounded by long thin filaments, where galaxies gather like morning dew along a thread of silk. It was immense. It was measurable. It was for a while enough. And then the numbers began to quietly disagree. It started not with a dramatic announcement, but with something far more modest, a persistent small discrepancy between what astronomers observed and what their calculations predicted. When researchers studied the way galaxies moved within clusters, the visible matter simply could not account for what was happening. There was not enough mass according to everything that could be seen to keep those clusters from flying apart, and yet they held together, steadily, patiently, without any apparent concern for what the equations said they should be doing. The Swiss-American astronomer Fritz Zwicky noticed this in the 1930s while studying a cluster of galaxies in the constellation Coma Berenices. He measured the velocities of the individual galaxies within the cluster and found that they were moving far too fast for the visible matter present to gravitationally contain them. He proposed that there must be additional unseen mass, what he called in the German of his notes dunkle Materie, dark matter, a quiet name for a quiet problem. For decades this idea remained on the margins. It seemed too strange, too speculative, an invisible ingredient added to make the sums work out. It may be that scientific communities, like most communities, find comfort in what can be directly observed. And the things Zwicky had proposed could not be seen, detected, or confirmed with any instrument then available. So the question waited. It waited through the 1940s and the 1950s and well into the following decade, carried forward by a small number of researchers who kept returning to those troubling numbers, those stubborn discrepancies that refused to resolve themselves. And then in the early 1970s something shifted. An astronomer named Vera Rubin, working with her colleague Kent Ford at the Carnegie Institution in Washington, began a careful and methodical study of how stars within individual galaxies move around their galactic centers. The expectation, based on everything that was understood about gravity and orbital mechanics at the time, was that stars further from the center of a galaxy should move more slowly than those closer in the same way that the outer planets of our solar system move more slowly than those near the Sun. This is simply how gravity works across distance. It was not a controversial prediction, It was almost assumed. What Rubin and Ford observed was something else entirely. The stars at the outer edges of galaxies were moving at nearly the same speed as those near the centre. Not slightly faster than expected, not marginally inconsistent, simply wrong in a very steady, very consistent and very repeatable way. Galaxy after galaxy showed the same flat rotation curve, the same quiet refusal to behave as visible matter alone would suggest. Something else was there. Evidence suggests it was not distributed the way visible matter is concentrated at the centre and thinning toward the edges. Instead, it seemed to form a vast and diffuse halo surrounding each galaxy, extending far beyond the visible disk of stars, holding everything gently in place from the outside. A presence felt entirely through its effects the way a current is felt not by seeing it, but by the way it moves everything around it. Vera Rubin spent years confirming this finding across dozens of galaxies, building a case so methodical and so consistent that it became eventually impossible to set aside. She did not announce it as a discovery of something dramatic. She simply noted what the data showed, returned to the telescope, and kept measuring. There is something in that patience worth sitting with for a moment. What researchers have built since then is a picture of the universe that is in some ways stranger and more generous than the one that came before it. The visible matter, the stars, the gas, the planets, every object that has ever emitted or reflected a single photon, accounts for only a small portion of the total mass of the cosmos. The larger portion, something in the range of 27 out of every 100 parts of everything, appears to be dark matter present everywhere, interacting with ordinary matter only through gravity, leaving no light, no radiation, no trace that any instrument has yet been able to directly confirm. It may be that this is the most fundamental thing about the universe, that what we can perceive of it is the exception, not the rule. That the glowing, visible, photon-emitting world we have always called reality is something closer to a thin and luminous skin over a much vaster, much quieter body. Scientists are still exploring what dark matter actually is. The leading candidates are hypothetical particles called weakly interacting massive particles, a name that describes their most essential quality, which is that they pass through almost everything without interaction, the way a thought sometimes passes through a room and leaves nothing behind. Other possibilities include axion, sterile neutrinos, and a range of other particles that exist so far only in theoretical space. None of them have been detected directly. What has been detected, mapped, and confirmed through multiple independent lines of evidence is the effect. The rotation of galaxies, the bending of light around invisible mass, the way galaxy clusters grow and move, the large-scale structure of the universe itself, which could not have formed in the way it did without the scaffolding of something unseen holding the early matter in place. There is an old way of understanding a forest that goes something like this. What you see when you stand inside one, the trunks, the canopy, the visible life moving through the light, is only the most recent layer. Beneath the soil root systems older than any individual tree extend through the dark in patterns no one has fully mapped. They share nutrients. They respond to each other. The visible forest rests in some essential way on an invisible one. What we understand so far suggests that the universe may work in something like the same way. The galaxies we see, the star-forming regions glowing softly across billions of light years, the slow spirals of gas and dust. All of it rests upon a structure that cannot be seen, an architecture of dark matter formed in the earliest moments of cosmic time that shaped the distribution of everything that would later become visible. It had been there long before the first star formed, long before light existed to illuminate anything, and in some quiet way it remains there now, holding the shape of everything we know. The question of what it is made of is still open. The question of whether we will ever detect it directly is still open. Researchers continue to design more sensitive instruments explore new theoretical models, consider possibilities that earlier generations of scientists had no framework to imagine. The search is ongoing, patient and almost entirely invisible to anyone not looking for it, which seems appropriate somehow. As you rest here in the particular stillness of this hour, there is something gently steadying about the idea that the universe contains far more than it reveals, that the visible portion, bright, measurable, familiar, floats within something larger and darker and fundamentally unknown. Not threatening, not demanding anything, simply present the way certain things are present in the night without being seen. And there is still more to this quiet architecture than the matter that cannot be found, because it turns out that matter, dark or otherwise, tells only part of the story. There is something else at work in the deep, something not pulling things together but pressing them slowly and steadily apart, something that makes up an even larger share of everything, something that has no name in ordinary experience and no analogy that fully fits. Researchers began to find traces of it not by looking for it, but by noticing carefully and with some confusion that the universe was not doing what it should have been doing. And what they found when they looked more closely changed everything they thought they understood about where all of this is going. There is a particular kind of knowing that arrives not through what something is, but through what it does. You cannot see the wind, but you can watch the way tall grass bends in a field, all of it tilting in the same direction at the same moment, and understand that something is moving through. You cannot see the depth of the cold water from the surface, but you can feel the temperature change as you descend and know without needing to see the bottom that something is down there. Science at its quietest and most careful often works this way, reading the behavior of visible things to understand what invisible ones must be doing. This is how the story of dark matter really begins. Not in a laboratory, not with a particle detected in a chamber or a signal received from space, but in the patient observation of how galaxies spin. When Vera Rubin sat with her rotation curves in the early 1970s, what she was looking at was not darkness itself. She was looking at starlight, the ordinary measurable light of stars orbiting within spiral galaxies plotted against their distance from the galactic center. The graph that should have emerged, based on everything that was understood about gravitational physics, would have sloped gently downward toward the edges, stars further out moving slower, a predictable curve like the arc of water falling from a height. What emerged instead was something almost flat. Stars at the edge moving nearly as fast as stars near the center, not approximately, not within a small margin of error, consistently, measurably, stubbornly flat, across one galaxy, then another, then dozens more, each one confirming the same quiet anomaly. Researchers who reviewed this data understood what it implied. Either the laws of gravity as understood at the time were incomplete, an unsettling possibility but one that had to be considered, or there was additional mass present in these galaxies that could not be seen. Mass distributed not in the bright disk of stars and gas at the center, but in a vast diffuse sphere extending far beyond the visible edges. A halo, a presence felt entirely through its pull. Evidence suggests that both possibilities were taken seriously for some years. The scientific community does not tend to abandon well-tested frameworks easily, and gravity, as described by Isaac Newton and later by Albert Einstein, had performed extraordinarily well across centuries of observation. The idea that a new invisible form of matter might be required was in some quarters considered the less conservative option, and yet the rotation curves persisted. New telescopes confirmed them. Independent teams replicated the findings. The data did not soften or resolve itself. It simply remained patient and flat, and eventually the weight of it became difficult to set aside. What scientists began to call this unseen presence, dark matter, accumulated evidence from multiple directions over the following decades, each line of observation arriving independently and pointing toward the same quiet conclusion. One of the most striking came not from individual galaxies, but from the way light itself bends. Einstein's general theory of relativity, confirmed in the early 20th century, describes gravity not as a force transmitted between objects, but as a curvature in the fabric of space and time. Massive objects bend this fabric, and light travelling through it follows the curve. This means that a massive object positioned between a distant light source and an observer will act like a lens, bending and magnifying the light that passes around it. A phenomenon called gravitational lensing. When astronomers began using this effect to map the distribution of mass in galaxy clusters, they found something quietly remarkable. The lensing was far stronger than the visible matter could account for. Light was bending around regions of space that appeared to every available instrument to be almost entirely empty. Something was there deflecting light curving space, something with mass, but without any of the properties of ordinary matter that would make it visible. It may be that this was the moment the case became for most researchers genuinely compelling. Here was dark matter leaving its signature not on the speed of stars, but on the path of light itself. Two completely independent phenomena observed with completely different instruments pointing toward the same invisible presence. The Bullet Cluster is one of the places where this evidence became most vivid. Located roughly 3.5 billion light-years away, the Bullet Cluster is actually two galaxy clusters that have passed through each other. A collision in cosmic terms, though one that unfolded over millions of years at speeds that would be difficult to hold in the mind. When two clusters of this kind collide, the ordinary gas and plasma between the galaxies which makes up most of the visible mass slows down through electromagnetic interactions and lags behind. The individual galaxies and whatever dark matter surrounds them pass through with much less resistance. When researchers mapped the Bullet Cluster, using both X-ray observations of the hot gas and gravitational lensing maps of the total mass, they found that these two distributions had separated. The visible matter, the hot gas glowing in X-ray light, sat clustered in the middle, still catching up. The gravitational mass, as revealed by the lensing, had moved ahead with the galaxies concentrated in two distinct regions on either side of the collision. The mass and the light were in different places. This is not what would happen if there were no dark matter or if gravity simply behaved differently at large scales. It is scientists suggest exactly what would happen if invisible weakly interacting matter were present alongside the visible kind, matter that passes through collisions the way fog passes through fog without friction, without delay, without leaving any light behind. What dark matter is made of remains genuinely open. The leading theoretical candidates have names that feel almost abstract when said aloud. Weakly interacting massive particles which physicists have searched for in detectors buried deep underground, placed where cosmic rays and ordinary radiation can barely reach. Axions far lighter, hypothetical particles originally proposed to resolve a different problem in particle physics entirely, which might be detectable through the way they interact with strong magnetic fields. Sterile neutrinos, ghost-like particles that interact even less than the ordinary neutrinos already known to pass through ordinary matter in enormous numbers every second. None of these have been directly detected. Experiments have run for years, for decades, in conditions of extraordinary quietness and precision, and returned results that are so far consistent with absence. What we understand so far suggests that dark matter, if it is a particle, is either lighter or heavier than the most popular models predicted, or interacts through channels that current experiments are not yet sensitive to. Scientists are still exploring whether dark matter might be something even stranger, not a single particle species, but an entire hidden sector of physics, a shadow world of particles and interactions that parallels our own but touches it only through gravity. It is a possibility that cannot yet be ruled out. There is something quietly humbling about that. The universe, it turns out, is made mostly of things that leave no light and no signal, that pass through walls and planets and the human body without slowing, without acknowledging the contact at all. The 5% that emits and absorbs photons, the matter from which everything we have ever touched or seen or measured is constructed, moves through a much vaster medium of invisible material that shapes the structure of everything around it without ever being directly known. Researchers have mapped the large-scale distribution of dark matter across hundreds of millions of light-years using gravitational lensing surveys, and what they find is something that resembles in its broad outlines a vast and intricate web. Long filaments of dark matter spanning enormous distances with knots at the intersections where galaxy clusters form. Between the filaments, immense voids, regions nearly empty of both dark and ordinary matter, vast and dark and quiet. The visible universe, with all its galaxies and stars and the ancient light that fills our night sky, sits within this web like something delicate held in a net so fine it cannot be seen. The light is real, the warmth of it, the beauty of it, the fact that it's been travelling for so long just to arrive here. All of it is real. It simply rests on something invisible, something patient, something that has been present since long before the first star thought to form, and the dark matter tells only part of the story. Because the 27% that dark matter represents and the 5% of ordinary visible matter together still fall short of the total, they account for roughly 32 parts in 100 of everything. The remaining 68% is something else entirely. Not matter at all, not something that pulls things together or holds galaxies in place or bends light around its presence. Something that pushes, something that expands, something that was discovered not by looking outward into space but by watching with great care how the most distant lights in the universe were moving, and finding in that quiet motion an answer that no one had been expecting, and that changed the shape of everything that came after. And what scientists discovered in that moment is something the night sky had been hinting at all along in the only language it knows, the slow ancient language of light moving steadily away. There is a kind of discovery that does not announce itself. It arrives quietly dressed as a confirmation of something already known, and only reveals its true nature in the gap between what was expected and what was actually found. The person holding the data does not always recognize it immediately. Sometimes the first response is to check the instruments, to run the numbers again, to look for the error because the error seems at first far more likely than the alternative. This is roughly what happened in the late years of the 1990s when two independent teams of astronomers set out to do something they believed was straightforward. They wanted to measure how fast the universe's expansion was slowing down, not whether it was slowing, that at the time was considered settled. The universe had been expanding since its earliest moments, and gravity, the mutual attraction of all matter for all other matter, was understood to be gradually pulling back on that expansion, the way friction gradually slows a wheel. The question the researchers were asking was only how much. How quickly was the expansion decelerating? What would the eventual fate of the universe be? It seemed like a measurement problem, a technical one, important certainly, but not the kind of work that changes the foundations of physics. The tool they used was a particular kind of exploding star. When a white dwarf, the dense cooling remnant of a star like our Sun, accumulates enough mass from a companion star to exceed a precise threshold, it undergoes a catastrophic thermonuclear explosion. This explosion, called a Type 1 supernova, releases an enormous and remarkably consistent amount of energy. Consistent enough that astronomers can use it as what they call a standard candle, a light source of known brightness, which means that by measuring how bright it appears from Earth, they can calculate how far away it is with considerable accuracy. By the middle of the 1990s, both teams had collected observations of Type 1 supernovae in distant galaxies, as some of them billions of light-years away. The plan was simple in principal measure. The apparent brightness of these distant explosions, calculate their distances, compare those distances to the recession velocities of their host galaxies, and from that comparison extract the rate at which the expansion of the universe was slowing. What they found was that the distant supernovae were fainter than expected. Fainter by a specific, measurable and deeply confusing amount. Fainter meant further away, and further away for a given recession velocity meant that the universe had been expanding more slowly in the past than the models predicted, which could only mean one thing. The expansion was not slowing down, it was speeding up. Researchers on both teams working independently cross-checked their data. They looked for systematic errors in their measurements of supernova brightness. They considered whether dust in distant galaxies might be dimming the light in some unexpected way. They reviewed their calibrations, their instruments, their assumptions about the physics of the explosions themselves. And when none of these investigations produced an alternative explanation, they did what careful scientists do when the data is consistent and the error cannot be found. They published. The results appeared in the year 1998, and the response from the broader scientific community was something between fascination and discomfort. The universe was not merely expanding, it was accelerating, growing larger at an ever-increasing rate, as if something were pushing space itself outward from within. Something that was not matter, not radiation, not anything that had been accounted for in the standard models of cosmology. It may be that the most unsettling discoveries are the ones that do not tell you what something is, but only that it must exist. The name that emerged for this unknown component, dark energy, was chosen partly for its parallel with dark matter, and partly because it's described as honestly as possible the state of knowledge at the time. Dark meant unknown. Energy referred to its effect on the dynamics of space. Beyond that, the name carried almost no information. What scientists suggest, based on everything that has been measured since, is that dark energy accounts for approximately 68 out of every 100 parts of the total content of the universe. If you were to take everything that exists, all the matter, dark or ordinary, all the radiation, all the gravitational and kinetic energy distributed across every galaxy and void and filament in the observable cosmos, and set it on some impossible scale, dark energy would outweigh all of it combined by a considerable margin. And yet no one has ever detected it directly. No instrument has measured it. No particle has been proposed that convincingly explains it. It reveals itself only through its effect on the expansion of space, the same way a breath reveals itself by the way it moves dust in the light. The simplest mathematical description available comes from a term that Albert Einstein himself introduced into his field equations in the year 1917, and then famously retracted. He had added it as a stabilizing factor, a kind of cosmic pressure that would balance the gravitational attraction of matter and produce a static, unchanging universe, which was the prevailing model at the time. When Edwin Hubble's observations established that the universe was in fact expanding, Einstein reportedly called this addition his greatest blunder and removed it from his equations. The term was called the cosmological constant, represented in the equations by the Greek letter lambda. When the supernova data arrived in 1998, researchers found that reintroducing this constant, with a value adjusted to match the observed acceleration, produced a model that fit the data remarkably well. The cosmological constant, reborn not as a stabilizer but as an accelerator, became the leading description of dark energy. What the constant physically represents is less certain. The most natural interpretation within quantum field theory is that it corresponds to the energy of the vacuum, the energy present in empty space itself, arising from the constant appearance and disappearance of virtual particles at scales too small for direct observation. When theorists calculate what this vacuum energy should be, However, they arrive at a number that differs from the observed value by somewhere in the range of 120 orders of magnitude. This is by some measures the largest discrepancy between theoretical prediction and experimental observation in the history of physics. Evidence suggests the problem is real and unresolved, and that it is pointing towards something important that is not yet understood. There are other proposals. Some researchers have suggested that dark energy is not a constant at all, but a field that changes over time, something they call quintessence, a dynamic energy distributed through space that evolves as the universe ages. If this were true, the rate of acceleration would not be steady, and sufficiently precise measurements of distant supernovae or of the distribution of galaxies across cosmic time might eventually detect a variation. Others have proposed that general relativity itself requires modification at cosmic scales, that gravity behaves differently across the vast distances of the universe than it does locally, and that what appears to be dark energy is actually a signature of this modified behavior. These models are technically complex and not yet strongly supported by observation, but they represent a genuine and ongoing area of inquiry. What we understand so far suggests that no single explanation has yet achieved anything close to consensus. The acceleration is real and confirmed by multiple independent methods. The supernova data, the pattern of the cosmic microwave background, the clustering of galaxies across billions of light years. The cause remains in the deepest sense unknown. There is something almost peaceful about that considered from a certain angle. The universe contains an energy that fills all of space, drives everything apart, and has done so for billions of years without once making itself available for examination. It does not interact with matter in any way that leaves a trace. It does not vary across regions or respond to the presence of mass. It simply persists evenly distributed through the fabric of space, pressing everything gently and continuously outward. In some cosmological models, this expansion will continue indefinitely, with galaxies beyond a certain distance eventually receding faster than light can cross the space between them, meaning they will become in principle unreachable and eventually unobservable. The universe in the very long run may become quieter and quieter in this way, not through any violence or collapse, but through a slow and gentle separation. Each cluster of galaxies eventually becoming its own small island in the dark, still turning, still burning, still quietly beautiful but no longer in any contact with what lies beyond. It is not an ending that feels abrupt. It feels, if anything, like a very slow exhale. And within all of this, the dark matter holding galaxies in their shapes, the dark energy pressing space continuously outward, the vast invisible architecture that surrounds the small bright fraction we have always called the universe. There is the question of where everything we can see actually came from, not in the distant future but at the very beginning. In the first moments after the universe began, when space itself was so dense and so hot that the matter we know could not yet exist in any form, when everything was one thing and then gradually became distinct. The story of what happened in that earliest time is written not in visible light, but in the faintest possible signal, a quiet glow still present in every direction of the sky, a remnant of something so old that the light from it has been travelling toward us since before the first star was ever born. Researchers have spent decades reading that signal, and what it tells them about the hidden architecture of the cosmos is something that arrives, like most of the best things in science, slowly and with a kind of wondering patience. Somewhere in the middle of the 17th century, a cartographer working in Amsterdam sat down to draw the world. He had access to the best information available. The reports of sailors, the sketches of explorers, the accumulated observations of people who had travelled to the edges of what was then considered known. He rendered coastlines with care, filled in the interiors of continents with what knowledge existed, and where knowledge did not exist, he made educated guesses. Some of these guesses were remarkably close to correct. Others placed mountain ranges in the middle of oceans, or drew rivers that bent in impossible directions, or filled the blank spaces of Africa and the Americas with creatures and kingdoms that no one had ever seen. The map was in its way beautiful, and it was also in large and significant portions wrong. What is interesting about those old maps is not the errors. It is the confidence with which the blank spaces were filled. The cartographer did not leave white space where knowledge ran out. He drew something. Because a map with blank space felt in some fundamental human way incomplete, unsettling, like an admission of not knowing that was harder to sit with than a comfortable approximation. Scientists suggest that something similar operated in our understanding of the universe for most of the 20th century. The visible cosmos, the stars and galaxies and luminous clouds of gas that instruments could detect, was mapped with increasing precision and confidence. And because it was so vast and so detailed and so full of astonishing structure, it was easy to assume it was more or less the whole picture. It was not the whole picture. It was not even close. Consider what the current inventory actually looks like held quietly in the mind. Ordinary matter, the kind made of protons and neutrons and electrons, the kind that forms every atom in every star, every planet, every living thing, every instrument ever built to look at the sky, accounts for approximately 5 out of every 100 parts of the total content of the universe. This is everything we have ever seen. Every photograph of a distant galaxy, every spectrum of starlight analyzed in a laboratory, every cosmic ray particle detected at the surface of the Earth, all of it together, 5%. Dark matter invisible and undetected, but inferred through its gravitational effects on visible things, makes up approximately 27% dark energy, the unknown component responsible for the accelerating expansion of space, accounts for approximately 68%. This means that roughly 95 out of every 100 parts of everything that exists is in the most honest sense of the word unknown, not merely unexplored, not simply unmapped in the way that the seafloor was unmapped before deep-sea instruments existed, fundamentally, genuinely, presently unknown, composed of something for which no direct evidence has yet been gathered and about which no confirmed theory yet exists. It may be that this is the most important number in all of modern cosmology, and also the one that receives the least comfortable amount of attention in everyday life. There is a useful way of sitting with a number like 95%, not as a statement of failure or as an admission that science has somehow missed the larger part of reality, but as a map with the majority of its space still blank. Honestly, accurately, intentionally blank, because blank is the truth, and the truth, even when it is mostly empty, is more valuable than a comfortable fiction drawn in the margins. Researchers have found that acknowledging what is not known is in many ways the most productive state a science can be in. The history of physics is full of moments where the blank spaces turned out to be where the most interesting things were hiding. The anomalous orbit of Mercury, which Newtonian mechanics could not quite account for, was a blank space that led to general relativity. The ultraviolet catastrophe in classical thermodynamics, a small and annoying discrepancy in how hot objects radiated energy, led to quantum mechanics. The persistent mystery of why the Earth was so much older than any plausible energy source for the Sun could explain led to the discovery of nuclear fusion. The blank spaces are not where science has failed, they are where science is most alive. What we understand so far suggests that the 95% is pointing towards something genuinely new. Not a small correction to existing models, but a fundamental expansion of what physics is able to describe. Something that may, when it arrives, change the picture as profoundly as those earlier discoveries changed theirs. What makes the current blank space particularly striking is that it's not evenly distributed. The large-scale structure of the universe, the distribution of galaxies across billions of light years, The filaments and voids and clusters of the cosmic web reflects the underlying distribution of dark matter. And this structure has been mapped with considerable precision through surveys that track the positions and velocities of hundreds of millions of galaxies. What these surveys reveal is a universe organized not randomly but with a deep and intricate pattern. The filaments of the cosmic web stretch across distances of hundreds of millions of light years, connecting clusters of galaxies at their intersections like knots in a net. Between the filaments' immense voids, regions nearly empty of both matter and galaxies, extend across volumes so large that the entire observable region of our own galaxy would be invisible at their scale. The voids are not nothing. Evidence suggests they contain a small amount of diffuse ordinary matter, some dark matter, and the ever-present dark energy. But they are by cosmic standards extraordinarily empty. Our own galaxy, the Milky Way, sits within a local group of perhaps 50 or 60 galaxies itself, located within a larger supercluster called Laniakea, a name drawn from Hawaiian meaning immeasurable heaven. Laniakea stretches across roughly 500 million light-years and contains something in the range of 100,000 galaxies. And even Laniakea, vast as it is, occupies only a small region of the observable universe, which itself extends across approximately 93 billion light-years in every direction. These numbers do not compress easily, they are not meant to. They are simply the dimensions of the place where everything we know is happening. What is worth sitting with slowly is the relationship between the visible and invisible components across this structure. The ordinary matter, the 5%, does not distribute itself randomly within the cosmic web. It follows the dark matter. It accumulates where dark matter accumulates, forming galaxies at the densest intersections of the invisible web, flowing along the filaments, avoiding the voids. The visible universe is in this sense a tracing of the invisible one, a luminous outline of a structure that exists independently of the light it has attracted. Researchers have run extraordinarily detailed computer simulations of cosmic structure formation, beginning from the conditions of the early universe, and evolving forward through 13.8 billion years of gravitational dynamics. These simulations, which require some of the largest computational resources available, produce virtual universes whose large-scale structure matches the observed distribution of galaxies with remarkable fidelity. When the dark matter component is removed from the simulations, the structure dissolves. The filaments do not form. The galaxies do not cluster in the right way. The visible universe as it actually exists cannot be reproduced without the invisible scaffolding that holds it. This is what it means to say that dark matter is not a correction to the picture. It is the picture's underlying architecture, the reason anything is where it is. There is a quality to the cosmic web that is quietly difficult to hold in ordinary thought. It is not the scale exactly, though the scale is extraordinary. It is more the combination of structure and emptiness. The way the filaments and nodes and voids together creates something that is in its geometry neither random nor regular, something patterned in a way that feels, when viewed in the visualizations that researchers have produced from survey data, almost organic, almost familiar. The same kind of pattern appears at very different scales in the architecture of neural networks in the brain. The branching and clustering of neurons across the cerebral cortex, connecting regions through long axonal pathways with dense nodes of connectivity, surrounded by quieter regions. It appears in the branching of river deltas viewed from above, in the mycelial networks of fungi spreading through soil, in the vascular systems of leaves. The similarity is not causal. There is no physical connection between the cosmic web and the structure of the brain. It may be that nature simply finds the same geometries useful across very different scales and very different physical processes, That branching, clustering, and connecting through sparse networks is simply an efficient way to organize things, whether those things are galaxies or neurons or water or fungal threads. But the resemblance is there, quiet and unforced, and worth noticing the way certain things are worth noticing at night. The map of the universe is mostly blank, and the blank parts are not failures of imagination or gaps to be filled with comfortable guesses. They are honest spaces held open by careful measurement, waiting for the kind of understanding that has not yet arrived. What scientists are still exploring is whether that understanding will come through new particles, new instruments, new theoretical frameworks, or some combination of all. The experiments currently running, the surveys mapping billions of galaxies, the detectors listening in underground silence, the space telescopes measuring the subtle distortions of light across cosmic distances, are all in their different ways tracing the edges of the blank space, trying to find where the drawing stops and the unknown begins. And sometimes in science, as in life, the most clarifying thing is not an answer but a more precise understanding of exactly where the question is. There is a layer beneath all of this that most accounts of dark matter and dark energy tend to move past quickly in the interest of reaching what is known. But it is worth slowing down here for a moment in the particular quiet of this hour. The universe has been expanding for nearly 14 billion years. In all that time, across all that distance, through all the formation of stars and galaxies and the slow chemical evolution that eventually produced the matter, from which awareness itself is made, the invisible components have simply been there, patient, unchanged in their nature if not in their distributor, not waiting for anything, not moving toward any particular outcome. Just present the way deep water is present beneath the surface of a still lake, not visible, not felt directly, but shaping the surface from below in ways that are real and continuous and older than anything floating on top. And what is most interesting about that invisible presence is not its strangeness, but the way it connects to something much closer. Something not in deep space at all, but in the immediate and local world of matter-light and the way ordinary things came to be the particular shapes they are. Because the cosmic web did not always look this way, it grew into this structure from something far simpler. A pattern of almost imperceptible variations in the earliest moments of the universe, variations so small they were thought for decades to be beyond any instrument's reach. And the story of how those variations were finally heard is one of the quietest, most patient achievements in the history of science. There is a version of this story that stays entirely in the sky. It moves from galaxy to galaxy, from supercluster to void, from the earliest light to the expanding edge of what is observable. It is a true story and a vast one, and it is easy to stay there in the cool distances where everything is measured in billions and the human scale feels pleasantly irrelevant. But there is another version of the same story, one that begins not out there but here. In the room where you are lying, in the particular weight of your body against whatever is beneath you, in the quiet that surrounds this hour. Because the invisible components of the universe are not only present in the deep reaches of space, they are present here too, right now, passing through the walls of this room, through the floor, through the air, through you continuously and without acknowledgement, as they have been doing since long before this building existed, since long before this planet formed, since long before the first complex molecules gathered themselves into something that could eventually become aware of being passed through. This is not a metaphor. It is as precisely as current physics can state it simply what is happening. Researchers have found that the Earth is moving through the galaxy at roughly 220 kilometers per second, orbiting the galactic center, along with every other star in the Milky Way. The galaxy itself is moving through the local group, and the local group is falling along with thousands of other galaxies toward the gravitational center of the Laniakea supercluster. Everything is in motion continuously through a medium that is mostly invisible. And through all of that motion, dark matter is passing. The leading theoretical models suggest that dark matter particles, whatever they ultimately are, fill the galaxy in a diffuse halo permeating the space between and around the stars. As the Earth moves through this halo, it encounters a continuous stream of these particles from a preferred direction, the direction of the Sun's motion through the galaxy. This means that in principle there should be a slight annual variation in the rate at which dark matter particles arrive at any given location on Earth, as the planet's orbital motion around the Sun either adds to or subtracts from the relative velocity. Several experiments have searched for exactly this signal. One of them, the Detector for Advanced Research and Production, in an underground laboratory, reported a periodic annual variation in their detection rate that has persisted across many years of observation. Whether this signal represents actual dark matter detection or some systematic effect in the instrument remains genuinely contested. Scientists are still exploring the data, and other experiments have not confirmed the finding. But the search itself rests on a real and measurable physical prediction that the invisible matter filling the galaxy should be flowing through this room right now at a calculable rate. The numbers involved are difficult to hold in ordinary imagination, but they are worth considering slowly. If the most widely discussed dark matter candidates, the weakly interacting massive particles, exist at the masses and interaction rates that theoretical models have historically favoured, then approximately 100,000 of them would be passing through every square centimetre of your body every second, not accumulating, not interacting, simply passing the way a thought passes through a room when no one is there to think it, each one carrying a small amount of kinetic energy, each one in the overwhelming majority of cases leaving no trace whatsoever in the atoms it moves through. Occasionally, very, very occasionally, such a particle might collide with an atomic nucleus, with enough force to cause the nucleus to recoil slightly. This recoil would release a tiny amount of energy, detectable in principle, which is the entire basis of every underground detector that has been quietly waiting in the dark for the past 3 decades. It may be that you have already been the site of such a collision. There is no way to know. The energy released would be far below the threshold of any biological process, far below anything that could be felt or measured by any medical instrument. It would happen if it happened in the same silence with which everything else about dark matter happens, unannounced, unrecorded, gone. There is something worth sitting with in that image for a moment. The body is used to being a boundary. The skin marks the edge of self and world. What is inside is interior. What is outside remains outside. This is a useful model for ordinary life and a deeply embedded one. But the physics of it is considerably more permissive. Neutrinos, particles produced in enormous quantities by the nuclear reactions in the Sun, pass through the Earth as if it were not there. Roughly 65 billion of them cross every square centimetre of the Earth's surface facing the Sun every second. At night they pass upwards through the planet from below. The Earth, from a neutrino's perspective, is not meaningfully denser than empty space. It offers almost no resistance. Dark matter, if it interacts even less than neutrinos, passes through with even less acknowledgement. What we understand so far suggests that the solid world, the felt-weighted physical world of matter and contact and resistance, is at the level of fundamental particles almost entirely empty space interrupted by very occasional points of electromagnetic interaction. The table that feels solid feels that way because its electrons repel the electrons in your hand. The electrons themselves are vanishingly small. The nuclei they orbit are smaller still and separated from one another by distances that, scaled up to human size, would place them miles apart. Everything that feels solid is in this sense a kind of agreement between electromagnetic fields. a mutual arrangement that creates the sensation of contact of surface of resistance. And through all of it, dark matter and neutrinos and cosmic rays and the ancient photons of the cosmic microwave background simply flow, observing none of these arrangements, touching none of these agreements. The cosmic microwave background is worth pausing on here, because it represents something unusual among the invisible things that surround us. Unlike dark matter, it is composed of ordinary photons, real electromagnetic radiation in principle detectable by the right instrument. What makes it remarkable is its age. In the first moments after the universe began, space was filled with a plasma so dense and so hot that light could not travel freely through it. Photons were constantly absorbed and re-emitted, scattered in every direction, unable to escape. The universe was opaque, the way fog is opaque, full of light but incapable of transmitting a clear image. This state persisted for approximately 380,000 years. Then, as the universe expanded and cooled to a temperature where electrons and protons could combine into neutral hydrogen atoms, the plasma cleared. Light was suddenly free to travel, and the light that was present at that moment, distributed with extraordinary uniformity across the entire visible universe, began its journey in all directions at once. That light is still travelling, stretched by the expansion of space from its original temperature of roughly 3,000 degrees to its current temperature of approximately 2.7 degrees above absolute zero. It now falls in the microwave portion of the electromagnetic spectrum. It arrives at Earth from every direction simultaneously, a nearly perfect sphere of ancient radiation surrounding the observable universe. Studies indicate that if your eyes were sensitive to microwave radiation rather than visible light, you would see the entire sky glow with this faint, even light, a relic of the moment the universe first became transparent. Not darkness, an ancient luminosity everywhere in all directions, the oldest light there is. That light carries information. Tiny variations in its temperature, fluctuations of roughly 1 part in 100,000, map the distribution of matter in the early universe. The slightly denser regions where matter was very marginally more concentrated correspond to the seeds of what would later become galaxy clusters. The slightly less dense regions correspond to what would become voids. Those variations are the reason the cosmic web has the structure it does, the reason galaxies are where they are, the reason there is something rather than a perfectly uniform and featureless distribution of matter across all of space. Dark matter already present at that early time amplified those fluctuations, gravitationally drawing matter toward the denser regions faster than ordinary matter alone could have. Without it, the variations in the cosmic microwave background would have been too small to grow into the structure the universe actually has. This is what it means in practical terms to say that dark matter shaped the universe, not as a distant or abstract influence, but as the mechanism by which almost imperceptible irregularities in the early cosmos were amplified into everything. Every galaxy, every star, every planet, every arrangement of molecules that eventually became capable of lying still in the dark and wondering about any of this. The room you're in was built from atoms forged in stars that formed within structures shaped by dark matter. The air moving gently through you was assembled from elements whose distribution across space reflects the cosmic web's underlying architecture. The very fact that there is something here, rather than a smooth and unstructured fog of particles spread evenly across a universe that never organized itself into anything, traces back to those early fluctuations amplified by an invisible presence into the intricate and particular world that eventually produced this moment. Evidence suggests that the connection between the invisible cosmos and the immediate physical bodily experience of being alive is not merely poetic, it is structural, causal. The product of billions of years of gravitational shaping that began with dark matter and ended, among other things, here, which is something worth resting alongside quietly without needing to follow it anywhere. There is a quieter layer to all of this, one that lives not in the deep history of matter, but in the way science itself sits with what it cannot yet explain in the long and patient work of listening for a signal that may not come in any expected form, and what that patience reveals about the nature of knowing. Because the instruments built to find dark matter are among the quietest places ever made by human hands, and the silence they have found there year after year is a particular kind of answer, one that the universe seems to be offering very deliberately, and that science is only beginning to learn how to read. There are places on Earth where the ground holds a memory that the surface has long forgotten. In certain parts of Greenland and Antarctica, ice cores pulled from depths of several kilometers contain air bubbles trapped hundreds of thousands of years ago. Tiny pockets of an ancient atmosphere preserved in the cold, carrying the chemical signature of a world that no longer exists. Scientists read these cores the way you might read a letter written before you were born, carefully, with the understanding that what is being held is fragile and irreplaceable and enormously old. The universe has its own version of this. It is called the cosmic microwave background, and it is not a record stored in ice or stone or any physical medium that can be handled. It is light, the oldest light that can be observed from Earth, photons released in the first moments when the universe became transparent, roughly 380,000 years after its beginning, now stretched by billions of years of expansion into the cool and gentle frequencies of the microwave spectrum. It is everywhere, arriving from every direction simultaneously, a sphere of ancient signal surrounding everything we can see, and within it, carried quietly across nearly 14 billion years, is the most detailed map of the early universe that physics has yet been able to read. To understand what was recorded in that light, it helps to spend a moment with what the universe was like before it was released. In the first fraction of a second after the beginning, the temperature of the universe was unimaginably high, conditions so extreme that the matter and energy we are familiar with did not yet exist in their current forms. As the universe expanded and cooled over the following minutes and hours, the lightest atomic nuclei formed hydrogen, helium, and trace amounts of lithium in proportions that cosmologists can predict with considerable precision and that match what is observed in the oldest stars. But for the next 380,000 years, the universe remained a plasma, a dense, hot mixture of nuclei and free electrons through which light could not travel freely. Every photon was almost immediately scattered. The universe was opaque in all directions, filled with energy, but incapable of transmitting information across any significant distance. During this period, something else was also happening. Ordinary matter and radiation were coupled together, oscillating. Regions of slightly higher density would begin to collapse under their own gravity, but the pressure of the radiation would push back, creating acoustic waves, pressure oscillations that traveled through the plasma at roughly half the speed of light, like sound waves moving through a fluid but at cosmic scales. Dark matter, which does not interact with radiation, did not participate in these oscillations. It simply sat within the regions of higher density, adding its gravitational pull without contributing to the pressure. Researchers have found that this combination, oscillating ordinary matter and radiation anchored by non-oscillating dark matter, left a very specific pattern of temperature variations in the plasma when it finally cleared. When the universe cooled enough for electrons to combine with nuclei into neutral atoms, the plasma cleared almost simultaneously across the entire observable universe. The photons that had been continuously scattered were suddenly free, and they carried outward in all directions a snapshot of the temperature and density of the plasma at that exact moment. That snapshot is what the cosmic microwave background preserves. Its temperature today is approximately 2.7 degrees above absolute zero, colder than any natural environment in the solar system, warmer than the coldest regions of deep space. It is remarkably uniform. If you mapped its temperature across the entire sky, The variations from one region to another would amount to roughly 1 part in 100,000, less than a 10,000th of a percent. But those tiny variations are not random. They carry the precise imprint of the acoustic oscillations in the early plasma modulated by the gravitational influence of dark matter. The pattern of peaks and troughs in the temperature map analysed through a mathematical technique called spherical harmonic decomposition, which extracts the characteristic angular scales at which the temperature variations are strongest, encodes information about the composition of the universe with extraordinary specificity. From this pattern, researchers can determine the ratio of ordinary matter to dark matter, the total energy density of the universe, the rate of its expansion, and the geometry of space itself. The Wilkinson Microwave Anisotropy Probe, launched in the year 2001, and the Planck satellite, launched in the year 2009, map this background radiation with increasing precision, and the results have been among the most precise measurements in all of cosmology. What those measurements confirm, among other things, is that the universe contains approximately 5 times more dark matter than ordinary matter, a ratio that has remained consistent across decades of independent measurement, from rotation curves to gravitational lensing to the large-scale structure of galaxies to the cosmic microwave background itself. There is something quietly remarkable about the chain of inference here. A temperature variation of 1 part in 100,000 preserved in the wavelength of photons that have been travelling for nearly 14 billion years contains enough information to determine the composition of the entire observable universe. The ratio of invisible matter to visible matter, the proportion of dark energy, the curvature of space on the largest scales. It may be that this is one of the most striking demonstrations of what physics at its best is capable of. Not the construction of large machines, though those have their place, but the reading of very faint signals, the patient attention to very small numbers, and the extraction from them of knowledge about things that cannot be directly seen or touched or approached. The light that carries this information has been travelling since before the first star existed. It passed through the empty space that would one day contain our galaxy, through the region that would one day become our solar system, through the thin atmosphere of a planet that did not yet exist, and eventually into instruments built by the descendants of single-celled organisms that had not yet evolved. And the information it carried intact across all of that time and distance told those descendants something true about where everything came from. There is a word for that kind of patience that does not quite exist in English, but it is felt sitting quietly with the idea in the particular stillness of very late at night. The acoustic oscillations in the early universe left a second signature as well, one that has only recently become accessible to observation. Because the oscillations were pressure waves moving through the plasma, they had a characteristic scale, the distance a sound wave could travel in the roughly 380,000 years before the plasma cleared. This distance, called the sound horizon, works out to approximately 490 million light-years in today's universe after expansion is accounted for. This scale is imprinted not only in the cosmic microwave background, but in the distribution of galaxies across space. Galaxies are slightly more likely to be separated from one another by approximately this distance than by slightly larger or smaller distances. A gentle excess in the 2-point correlation function of the galaxy distribution that statisticians and cosmologists call baryon acoustic oscillations. Studies indicate that this signal has now been detected in multiple large galaxy surveys, and it serves as a standard ruler in the universe, a known physical scale against which the expansion history of the cosmos can be measured. By observing how the angular size of this preferred separation changes with redshift with distance, researchers can trace how the expansion rate has evolved over billions of years, providing an independent check on the supernova measurements that first revealed the acceleration. What the two methods agree on, checked against the cosmic microwave background and against the growth of large-scale structure, is a universe whose composition and expansion history are consistent with approximately 5% ordinary matter, 27% dark matter and 68% dark energy. Not an approximation, not a rough estimate. A precise and internally consistent picture confirmed by 4 or 5 independent lines of evidence, each measuring different physical phenomena across different cosmic epochs. The sound of the early universe, those acoustic waves in the plasma moving at half the speed of light for 380,000 years, is encoded in both the light that surrounds us in every direction and in the positions of galaxies across the largest maps humanity has ever made. It is not a sound that can be heard, it is a pattern, a rhythm imprinted on space itself. But the fact that it was there, that the early universe was in some real physical sense, ringing, sustaining pressure oscillations across scales of millions of light years, is a strange and gentle thing to hold in the mind at night. What we understand so far suggests that the universe was not silent at its beginning. It was full of motion, of oscillation, of energy moving in waves through matter. And then at the moment it cleared, all of that motion was frozen into light, sent outward in every direction, preserved almost perfectly across billions of years, arriving here into instruments, into understanding, into this quiet hour. Evidence suggests that the full picture written in the cosmic microwave background is not yet completely read. The polarization of the background radiation, the way the electric field of those ancient photons is oriented, contains information about the very earliest moments of the universe, potentially including signals from gravitational waves produced during a period of rapid expansion called inflation, which may have occurred in the first fraction of a second. These signals, called primordial B-mode polarization, have not yet been convincingly detected, though several experiments are currently searching for them with increasing sensitivity. The early universe still has things to say, the light carrying those messages is already here, the instruments capable of reading them are being built and refined, and what they might reveal about the very first moments of time, about the physical process that set everything else in motion, remains one of the genuinely open questions in all of modern cosmology. There are still quiet things in this light waiting to be noticed, and the light itself, of course, is only one kind of messenger. There is another kind of signal that has been passing through the universe since its earliest moments, one that travels not as electromagnetic radiation, but as a distortion in space itself. One that was first predicted in the early 20th century and only directly detected in the second decade of the 21st. One that arrives from collisions and mergers and collapses happening across enormous distances, carrying information about events that no light could have escaped to tell us about. The story of how those signals were found and what they revealed about the hidden architecture of the cosmos is one of the most patient and precise achievements in the history of science, built in some of the quietest places ever constructed by people who were willing to wait decades for a signal that would last less than a second. There is a mine in the Black Hills of South Dakota that has not produced gold in many years. It goes by the name Homestake, and for nearly a century it was one of the deepest and most productive gold mines in the Western Hemisphere, its tunnels descending more than 1.5 miles below the surface of the Earth, following the veins of ore through ancient Precambrian rock. When the gold ran out and the mine closed in the year 2002, it might have simply sealed itself and faded into the particular quiet of abandoned industrial places. Instead, it became something else. Something that requires even more stillness than a closed mine. Scientists converted the deepest chambers of Homestake into a laboratory, not for chemistry or geology or the analysis of extracted minerals, but for something considerably stranger, the detection of particles that have never been seen moving through matter, that offers them almost no resistance, arriving from a direction no telescope can point. The facility is now called the Sanford Underground Research Facility, and it sits nearly 1.5 miles beneath the South Dakota prairie, surrounded by rock old enough to have formed before the first complex life appeared on Earth. The rock is not incidental, it is the point. To understand why the deepest possible quiet is necessary, it helps to consider the problem these experiments face. Dark matter particles on all current theoretical models interact with ordinary matter extraordinarily rarely. The rate at which they are expected to collide with an atomic nucleus, which is the only kind of interaction that most detectors are designed to catch, is so low that a single kilogram of detector material might experience only a handful of such collisions per year, or perhaps none at all. The signal, if it exists, is almost imperceptibly faint, and the background noise at the surface of the Earth is overwhelming. Cosmic rays, high-energy particles arriving from space produced by supernovae and other energetic events throughout the galaxy, strike the upper atmosphere, continuously producing cascades of secondary particles that shower down to the surface. Natural radioactivity in rocks and soil and building materials releases alpha and beta and gamma radiation constantly. Even the human body contains traceable amounts of radioactive potassium and carbon, and emits a small but measurable flux of radiation simply by existing. All of this background would completely swamp any dark matter signal at the surface. The faint collision of a dark matter particle with the nucleus, releasing an amount of energy roughly equivalent to a billiard ball striking another billiard ball at extremely low speed, would be indistinguishable from the continuous noise of background radiation. The solution is to go down, deep enough that the rock above absorbs the cosmic ray flux, deep enough that the only things reaching the detector are particles that interact so rarely with matter that even a mile of solid rock cannot stop them. At the depth of the Sanford facility, the cosmic Raymond flux is reduced by a factor of roughly 1,000,000 compared to the surface. What remains is mostly neutrinos and dark matter if it exists. The detector at the center of this facility is called Lux Zeppelin, which stands for Large Underground Xenon, Zeptoscale Effective Integrated Observatory, though the name matters less than what it contains. At its core is a vessel holding approximately 10 tons of liquid xenon, a noble gas cooled to minus 100 degrees Celsius, chosen because it is remarkably pure, because it produces a measurable flash of light when a particle deposits energy in it, and because its heavy nuclei are good targets for the kind of nuclear recoil that a dark matter collision would produce. The xenon is surrounded by layers of shielding water tanks, copper polyethylene, designed to absorb any remaining background radiation before it reaches the sensitive interior. When a particle interacts within the xenon, it produces two signals. The first is a prompt flash of ultraviolet light scintillation produced at the interaction point. The second is a delayed pulse of light produced when the ionization electrons drifting upward through the liquid xenon under an applied electric field reach the gas phase above and produce a second flash through electroluminescence. The ratio of these two signals and their precise timing allows researchers to distinguish between different types of interactions and in principle between the nuclear recoils expected from dark matter and the electron recoils produced by most background events. The entire apparatus operates in extraordinary quiet. The xenon is purified to levels of contamination measured in parts per trillion. The materials used in construction were selected, screened, and sometimes stored underground for years before used to allow naturally occurring radioactive isotopes to decay. The water surrounding the detector serves both as shielding and as a veto detector if a particle is registered in the outer water tank at the same time as a signal in the xenon. The event is rejected as background. What we understand so far suggests that this level of care is necessary not because the experimenters are being overly cautious, but because the signal they are looking for may be this quiet or quieter. Every unnecessary atom of radioactivity in the detector is a potential false positive. Every background event that passes through unnoticed is a potential confusion. The silence has to be nearly absolute before the faintest possible signal has any chance of being heard. The experiment has been running in various forms since before it reached its current configuration. The predecessor experiments the Large Underground Xenon Detector, and before that smaller prototype devices ran for years and found nothing inconsistent with background. Each null result was not a failure but a measurement, an increasingly precise statement about where dark matter is not and at what interaction rates it cannot be hiding. This is a form of knowledge that is easy to undervalue. When a search finds nothing, the natural human response is disappointment, the sense that the work produced no answer. But in physics, a precise null result is a real answer. It says whatever dark matter is, it does not interact with ordinary nuclei at this rate, at this mass, through this channel. It rules out an enormous region of theoretical space that was previously open. It forces theorists to reconsider their models, to look at other possibilities, to think more carefully about what assumptions they were making. Researchers have found that the history of physics is full of productive null results. The Michelson-Morley experiment of the late 19th century, which failed to detect the expected motion of the Earth through the luminiferous ether, was initially regarded as a failure. It eventually became foundational to special relativity. The absence of the signal was the signal. The search for dark matter is not only happening underground. At the European Organization for Nuclear Research near Geneva, where two intersecting circular tunnels running 27 kilometers in circumference accelerate protons to within a fraction of a percent of the speed of light, researchers have been searching for dark matter in a completely different way. When protons collide at the energies achieved in the Large Hadron Collider, the collision produces a shower of particles. If dark matter particles can be produced in such collisions, which they would be, if they have any coupling to ordinary matter, through any of the proposed theoretical channels, they would escape the detector without leaving any signal carrying away momentum that would show up as a measurable imbalance in the observed particles. Physicists call this missing transverse energy, and it is one of the signatures they search for in the enormous datasets produced by the collider's detectors. So far, no convincing evidence of dark matter production has emerged from the collider data. Like the underground detectors, the collider experiments have returned a result that is precise and informative. Dark matter, if it exists at the mass ranges most extensively explored, does not couple to ordinary particles through the channels that theoretical models had most commonly predicted. Evidence suggests that either dark matter is lighter or heavier than most models expected, or it couples through channels that are more difficult to produce at collider energies, or it is something fundamentally different from any particle that has been seriously theorized. There is a third kind of search that happens not on Earth at all but in space. If dark matter particles occasionally annihilate with one another, when they meet in regions of high density, as some theoretical models predict, the annihilation would produce ordinary particles as byproducts, gamma rays, positrons, antiprotons, neutrinos. These would be detectable in principle by space-based instruments orbiting above the Earth's atmosphere. The Fermi Gamma Ray Space Telescope has been scanning the sky for exactly these signals since the year 2008, looking particularly at the center of the Milky Way galaxy, where the dark matter density is expected to be highest, and at dwarf spheroidal galaxies orbiting the Milky Way, which are believed to be among the most dark matter-dominated objects in the local universe. Some analyses of the Fermi data have found an excess of gamma rays near the galactic center that is consistent with what annihilating dark matter might produce. Others have argued that the excess can be explained by other astrophysical sources, dense populations of rapidly rotating neutron stars called millisecond pulsars, for example. Scientists are still exploring this question. The signal is real. Its interpretation is not settled, and that uncertainty is not a flaw in the science. It is simply where the science currently is honest and precise about what it knows and what it does not. What is worth pausing on in all of this is the quality of attention that these experiments represent. The people who built the Sanford facility descended into a closed gold mine, cleaned its deepest chambers to a standard of purity that almost no natural environment on Earth achieves, and filled them with 10 tons of liquid noble gas cooled to extreme temperatures, surrounded by layers of shielding, selected atom by atom for their lack of radioactivity, and then waited. They are still waiting. The detector runs continuously, recording every event above its threshold, processing millions of triggers per year, setting aside the overwhelming majority as background and looking always for the rare and quiet thing that should not be there. This is a particular kind of patience that most descriptions of science tend to skip over: the years of running, the months of calibration, the careful and unglamorous work of understanding an instrument well enough to trust its silences as much as its signals. It requires a tolerance for not knowing, a willingness to sit with an open question for years that is not so different from other kinds of long patience. It may be that the qualities required to search for dark matter are not so different from the qualities required to sit quietly in the dark and simply rest. A willingness to stop expecting a particular answer, an openness to whatever the silence actually contains, a kind of settled attention that neither rushes toward resolution nor turns away from the uncertainty. The detectors are still running. The rock above them is still 3/4 of a mile thick. The xenon is still cold, still pure, still listening. And what the silence has been saying in its own way is that dark matter, whatever it is not what the simplest models predicted. It is either lighter or heavier or stranger or more weakly coupled than the most popular theories assumed, which opens a space in the science that is genuinely interesting. Not a failure of understanding, but an invitation to think differently, to consider possibilities that were set aside when the popular candidates seemed so promising, to ask whether the question itself has been framed in the most useful way. Some of those alternative framings have been sitting quietly at the edges of the field for years, not discarded but not fully explored, waiting for the mainstream searches to finish ruling out what they were built to rule out. And what some of those alternative possibilities suggest about the nature of dark matter is something that the silence of the detectors in a way has been pointing toward all along. There is a story told sometimes in the philosophy of science about a man searching for his keys under a streetlight. A neighbour finds him there on his hands and knees in the pool of yellow light and asks what he's looking for. The man explains. The neighbour asks, "Is this where you dropped them?" And the man says, "No, I dropped them over there in the dark, but the light is better here." It is a gentle story, not a criticism, just an observation about how searching works and about the gap that can open up between where the tools are pointed and where the answer might actually be. Scientists who work on dark matter have been thinking about this story in various forms for the better part of 2 decades. Not because the searches have been poorly designed, they've been extraordinarily well designed, but because the silence the searches have returned is long enough now and precise enough that it's beginning to say something meaningful about the shape of the problem. What it may be saying is that the most popular models were pointed at the right darkness, but perhaps not at the right depth within it. The dominant framework for dark matter for much of the late 20th century was elegant in its simplicity. Theorists working on a different problem entirely, the mathematical inconsistency in the standard model of particle physics known as the hierarchy problem, which concerns why the mass of the Higgs boson is so much smaller than theoretical expectations, proposed a class of extensions to the standard model called supersymmetry. Supersymmetry posits that every known particle has a corresponding partner particle with different spin properties. These partner particles, if they exist, would have been produced in abundance in the hot early universe, and the lightest of them, Stable, massive, and interacting with ordinary matter only through the weak nuclear force would have survived as a relic to the present day. This lightest supersymmetric particle, whatever specific form it might take in any given version of the theory, would be electrically neutral. It would be massive, somewhere between 10 and 1,000 times the mass of a proton. It would interact with ordinary matter so rarely that it would pass through almost anything without leaving a trace. And it would have been produced in the early universe in exactly the right abundance through a thermal process to account for the observed dark matter density. This coincidence that a particle proposed for completely independent reasons in particle physics would naturally produce the right dark matter. Abundance was called the weakly interacting massive particle miracle. It was and remains one of the most aesthetically compelling coincidences in modern theoretical physics. Researchers built experiments specifically designed to find this particle. Detectors optimized for its expected mass range. Collider searches tuned to its predicted production channels. Space-based instruments looking for the specific gamma-ray energies its annihilation would produce. And the particle has not appeared. This absence, accumulated across decades and dozens of experiments, has been absorbed differently by different people within the field. Some researchers maintain that supersymmetric dark matter remains the most theoretically motivated candidate, and that the experiments have simply not yet reached the sensitivity or mass range where it will be found. The parameter space, they note, is large, and the searches have covered only portions of it. It may be that the lightest supersymmetric particle is heavier than most searchers assumed, or couples to ordinary matter through a channel that has been less thoroughly explored. Others have drawn a different conclusion. They suggest that the consistent absence of the expected signal across experiments of increasing sensitivity and collider energies higher than any previously achieved is itself informative that it is pointing away from the simple supersymmetric candidates and towards something else. What we understand so far suggests that the field has, over the past decade or so, genuinely broadened. Alternative candidates that were once considered peripheral have moved closer to the center of serious investigation. The silence of the detectors has been productive in this sense, in a way that a positive detection might not have been, because a detection would have ended the search while the absence has expanded it. One of the most actively explored alternative frameworks is the idea of axions. The axion was not originally proposed as a dark matter candidate. It arose in the late 1970s from the work of Roberta Peccei and Helen Quinn, who were attempting to resolve a different theoretical puzzle. Why the strong nuclear force which governs the interactions between quarks does not appear to violate a symmetry called charge parity symmetry, even though the equations of quantum chromodynamics allow it to. Their solution introduced a new field, and the axion is the particle associated with the oscillations of that field. Very shortly after the axion was proposed, several physicists independently realized that if it exists and has certain properties, it would have been produced in the early universe in large quantities, would be extremely light, perhaps a billionth of the mass of an electron, and would behave in large-scale terms as cold dark matter. Not because anyone designed it that way, but because the mathematics of the Peccei-Quinn mechanism produces it naturally. The axion, if it exists, would be extraordinarily difficult to detect. Its interactions with ordinary matter are vastly weaker than those of the weakly interacting massive particle candidates. But it does have one exploitable property in the presence of a strong magnetic field. It can occasionally convert into a photon of a specific frequency determined by its mass. This process, axion-photon conversion, is the basis of a class of detectors called haloscopes, which are essentially microwave resonance cavities tuned to the frequency that an axion of a particular mass would produce. The axion dark matter experiment running at the University of Washington has been searching for this signal across a range of axion masses using a strong magnetic field and a resonant cavity cooled to temperatures close to absolute zero to reduce thermal noise. It has not yet found the signal, but it has excluded specific axion masses with the precision required to make meaningful theoretical statements, and its sensitivity is improving steadily as new resonator technologies are developed. Evidence suggests that search for actions is entering a period of genuine experimental maturity, where the instruments are finally approaching the sensitivity required to test the most theoretically motivated mass ranges. There is a third possibility that sits at a different angle from the others entirely. Rather than modifying the invisible content of the universe, some researchers have asked whether modifying the law of gravity itself might remove the need for dark matter altogether. Mordechai Milgrom, an Israeli physicist, proposed in the early 1980s that Newton's law of gravity might break down at the very low accelerations characteristic of the outer regions of galaxies. In his framework called modified Newtonian dynamics, gravity at low accelerations is slightly stronger than the inverse square law predicts, just enough stronger to explain flat rotation curves without any additional invisible matter. The proposal fits the rotation curves of many individual galaxies with surprising precision. It also makes predictions about the relationship between the visible matter content of a galaxy and its rotation speed predictions that researchers have found are observed to hold across a wide range of galaxy types and sizes in a relationship called the radial acceleration relation. The tightness of this relation, its low scatter across galaxies of very different morphologies and environments, is something that standard dark matter models find somewhat difficult to explain naturally. But modified Newtonian dynamics faces serious challenges at larger scales. It struggles to account for the observed properties of galaxy clusters without some additional dark matter. It does not easily produce the large-scale structure of the universe, the cosmic web, the clustering of galaxies across hundreds of millions of light years that standard cosmology reproduces with such fidelity. And the bullet cluster, where the gravitational mass and the visible matter are in different locations after a cluster collision, is difficult to explain without actual invisible matter present. It may be that modified Newtonian dynamics is capturing something real about the behavior of gravity at low accelerations while still missing a larger picture. Some researchers have developed relativistic extensions of the idea theories with names like tensor, vector, scalar gravity, and covariant emergent gravity that attempt to account for the cosmological evidence while preserving the galactic scale successes. Scientists are still exploring whether any of these frameworks can simultaneously explain everything that the dark matter hypothesis explains. The honest answer at the moment is that none of them quite do, but neither does any dark matter candidate explain everything cleanly. The field is in a state of productive uncertainty, which is not a comfortable state, but it is an honest one, and often the most interesting one. There is one more possibility worth sitting with quietly before moving on. Primordial black holes that formed not from the collapse of stars, but from density fluctuations in the very early universe. In the first fractions of a second after the beginning, were proposed as dark matter candidates decades ago, and then largely set aside when theoretical arguments suggested that most of the relevant mass ranges had been excluded. Recent gravitational wave detections beginning in the year 2015 have renewed interest in this possibility. The black holes whose mergers have been detected by the Laser Interferometer Gravitational Wave Observatory are in several cases heavier than the black holes that stellar evolution was thought to produce. Some researchers have suggested that primordial black holes in a particular mass range roughly between 10 and a few hundred times the mass of the Sun could account for some or all of the observed dark matter, and that the gravitational wave detections are glimpses of this population. Studies indicate that the evidence remains inconclusive. Certain mass ranges for primordial black holes have been excluded through careful observations of gravitational lensing, the distribution of cosmic microwave background fluctuations, and the abundance of small-scale structure. Others remain open. The question of whether primordial black holes contribute meaningfully to the dark matter budget is one that ongoing gravitational wave surveys and future space-based detectors may eventually be able to answer more definitively. What all of these alternatives share taken together is a kind of intellectual generosity toward the unknown. The field of dark matter research has in recent years become more genuinely open than it was during the period when supersymmetric candidates seemed to be converging on an answer, more willing to sit with multiple possibilities simultaneously, more comfortable holding the question without forcing it toward a resolution that the data does not yet support. Psychologists often note that the ability to tolerate uncertainty, to remain engaged with a problem without prematurely closing on an answer, is associated with some of the most creative and productive states of human cognition. It requires a kind of trust that the process itself is worthwhile, even when the destination is not yet in view. The people searching for dark matter in all its possible forms seem to have arrived at something like this state. Not from choice exactly, but from the accumulated experience of looking carefully in many directions for a long time and finding that the universe is more patient than any particular theory about it. There is a quality to all of this. The wide-open question, the multiple possibilities held simultaneously, the patient searching without a settled answer that feels at this hour strangely restful. Not because not knowing is comfortable, but because the not knowing is honest. And there is something in honesty, even incomplete honesty, even honesty that amounts mostly to a long and carefully maintained silence that the body recognizes as trustworthy. The universe does not owe anyone a legible answer on any particular schedule. It has been carrying these invisible components for nearly 14 billion years without explaining them to anyone. It seems in its quiet way perfectly comfortable with that. The mind, it seems, has been keeping something still and patient all along, and what emerges next is not another search in the dark, but something closer to what it feels like to stop searching and to simply notice what is already there. There is a particular quality to the hours after midnight that most people recognize without being able to name precisely. The thinking slows, the edges of things soften. Problems that felt urgent in the afternoon become not solved exactly, but somehow less sharp, held at a greater distance as if the mind has quietly decided to set them down for a while. The body grows heavier against whatever is beneath it. The breath lengthens and ends without any decision being made. Something is happening in these hours, something specific and measurable and deeply biological. And it turns out that what is happening in the neurons in the fluid surrounding them, in the slow oscillating rhythms of the sleeping brain, connects in ways that are not merely metaphorical to the same fundamental questions about invisible structure and hidden process that have been moving through this whole quiet night. The brain researchers have found is not a passive organ during sleep. It is in certain respects more organized, more actively engaged in specific processes than it is during much of waking life. The stillness of the body is not a stillness of the brain. It is more like the stillness of deep water, a surface calm over a great deal of invisible motion. The story begins with a system that was not known to exist until relatively recently. For most of the 20th century, the brain was understood to clear its metabolic waste, the byproducts of the intense biochemical activity that underlies all thought and perception, through the same lymphatic system that serves the rest of the body. But the lymphatic system does not in fact extend into the brain. The brain is separated from the rest of the body by the blood-brain barrier, a selective membrane that controls with great precision what enters and exits the neural tissue. In the year 2013, a neuroscientist named Mayken Nedergaard and her colleagues at the University of Rochester published a paper describing a previously unknown system of fluid channels in the brain running alongside the blood vessels through which cerebrospinal fluid circulates during sleep. They named it the glymphatic system, a portmanteau of glial and lymphatic, reflecting the fact that it is formed by a type of brain cell called astrocytes, which swell and contract to drive the fluid flow. What this system does, neuroscientists have observed, is remarkable. During sleep, the spaces between brain cells expand by roughly 60%, compared to the waking state, allowing cerebrospinal fluid to flow more freely through the tissue and flush out metabolic waste products that have accumulated during the day. Among these waste products is a protein called amyloid beta, the same protein that forms the plaques associated with Alzheimer's disease. Sleep on this account is not a pause in the brain's activity. It is, among other things, a cleaning cycle, a maintenance process that the brain cannot efficiently perform while simultaneously managing the demands of wakefulness. The body lying still in the dark is engaged without any awareness of it in the removal of molecular debris from its most complex organ. This is worth staying with for a moment, not as a medical fact, but as a kind of image. While the conscious mind is absent, or rather occupied elsewhere in the non-linear narratives of dreaming, the physical brain is engaged in a slow and thoroughgoing housekeeping. Fluid moving through channels that are invisible to ordinary awareness, carrying away what is no longer needed. Preparing the tissue for another day of perception and thought, and all the quiet work that consciousness requires. It may be that the parallel to the invisible structure of the universe is not forced. Both involve processes that are real and consequential and ongoing, yet entirely outside the reach of ordinary perception. Both involve a hidden architecture doing essential work beneath the surface that gives no indication of it. The 5% of the universe that emits light is maintained in its structure by the 95% that does not. The conscious experience of a person moving through a day is maintained in its clarity by a cleaning process that only runs when consciousness steps aside. The invisible is not the absence of the real. In both cases, it is closer to the condition that makes the visible possible. The glymphatic system is not the only hidden process running through the sleeping brain. Researchers have found that sleep organizes itself into cycles of roughly 90 minutes each, containing distinct phases with different electrical signatures, different hormonal environments, and different functional roles. The deepest phases, slow-wave sleep, or what sleep scientists sometimes call non-rapid eye movement stage 3, are characterized by large, slow oscillations in the electrical activity of the cortex with frequencies below 1 Hz. These slow waves, which can be measured at the surface of the scalp using electroencephalography, represent the synchronous end, firing and resting of large populations of neurons across the cortex. During these slow oscillations, something specific is happening in the hippocampus, the brain region, most associated with the formation of new memories. The hippocampus replays in compressed form the neural patterns associated with experiences from the preceding day. This replay, detected in rodents and subsequently inferred in humans through various indirect measurements, appears to be part of the process by which memories are transferred from short-term storage in the hippocampus to longer-term representations distributed across the cortex. Evidence suggests that this transfer is not simply a copying process. It involves a reorganization and extraction of patterns, relationships, and abstractions from the raw, experiential data of the day. The brain during slow-wave sleep is not merely archiving, it is in some sense interpreting, finding the structure within the accumulation, deciding through processes that have no access to conscious deliberation what to keep, what to consolidate, and how to connect the new to what was already known. The specific mechanism involves a conversation between the hippocampus and the cortex, mediated by distinct rhythmic patterns that appear to be precisely coordinated. Studies indicate that during slow-wave sleep, sharp-wave ripples in the hippocampus, brief high-frequency bursts of neural activity lasting roughly 100 milliseconds, occur preferentially during the quiet phase of the cortical slow oscillation, when neurons are temporarily inhibited. These ripples appear to drive the replay of recent experiences. Simultaneously, a slower rhythm called a sleep spindle, A burst of activity at 12 to 15 Hz lasting 1 to 3 seconds appears to be generated by the thalamus and may serve as a gating mechanism, allowing hippocampal signals to be received and incorporated by the cortex during the active phase of the slow oscillation. The coordination of these rhythms, slow cortical oscillation, hippocampal sharp wave ripple, thalamic sleep spindle, occurring in a precise temporal sequence creates a window during which information can flow from the hippocampus to the cortex and be integrated into long-term storage. It is an intricate and beautifully timed process running automatically without instruction in a brain that is by all external appearances simply resting. What we understand so far suggests that disrupting this sequence through fragmented sleep or sleep that does not include sufficient slow-wave phases impairs memory consolidation in measurable ways. The conversations between hippocampus and cortex are not completed. The memories are retained in a more fragile, more context-dependent form. The brain has not had the opportunity to do the organizational work that sleep was designed to perform. There is something in the image of the sleeping brain, this intricate electrical conversation happening in perfect darkness, organizing the residue of experience into something more durable and more connected that feels worth sitting with slowly. The brain does not know it is doing this. The person lying still has no access to the process. There is no sensation of filing, no experience of consolidation, no awareness of the slow waves moving through the cortex, or the sharp bursts of hippocampal replay, or the precisely timed spindles gating information across neural regions. It all happens behind the closed door of consciousness in the particular privacy of the sleeping brain's interior, and yet it shapes profoundly what the person carries forward. The things remembered clearly in the weeks and months and years after an experience are in part the things that sleep selected for consolidation. The insights that arrive unexpectedly the morning after a problem has been worked on intensively. Researchers suggest partly the product of the reorganization that sleep performed on the material. The feeling of clarity that follows a full night of rest is not merely the absence of fatigue. It is the presence of something that was built quietly and without any awareness during the hours of apparent stillness. The sleeping brain also does something with the emotional content of experience that is distinct from its handling of factual memory. Rapid eye movement sleep. The phase most associated with vivid dreaming appears to play a particular role in the processing of emotionally significant events. The neuroscientist Matthew Walker and his colleagues have proposed a model in which rapid eye movement sleep serves as a kind of overnight therapy. The brain replays emotionally charged memories in a neurochemical environment characterized by low levels of norepinephrine, the stress-related neuromodulator. This reduced norepinephrine environment may allow the memory to be processed and reconsolidated without the full emotional charge it carried at the time of the original experience. The brain tends to return to difficult or significant memories during rapid eye movement sleep, not to rehearse them, but to strip them of some of their urgency, to retain the content of the experience while softening its emotional sharpness. The memory does not change, but the relationship to it does. It becomes over successive nights of healthy sleep, something that can be held more calmly, something that has been integrated rather than merely stored. This is not a metaphor. It is a measurable neurochemical process with observable consequences for how emotionally significant memories are represented and experienced over time. Psychologists often note that the inability to sleep following a distressing event tends to preserve the emotional intensity of the event in its most raw form. The sleepless brain does not have access to the processing that rapid eye movement sleep provides. It holds the difficult experience at full charge, unprocessed exactly as it was encoded. Sleep, when it eventually comes, begins the work of metabolizing the emotional content, not erasing it, but transforming it into something the person can carry without being continuously overwhelmed by it. The body knows this in the way the body knows things not through understanding, but through the automatic wisdom of systems that have been refined across millions of years of evolution. The impulse to sleep after grief or shock or prolonged stress is not weakness. It is the brain asking for the time and conditions it needs to do the work that only it can do, in the quiet away from the demands of waking consciousness. It may be that lying still in the dark in this particular hour is itself a form of trust. Not a dramatic or deliberate trust, just the ordinary biological trust of a body that has released the day's accumulation of tension and is allowing the invisible processes to begin. The glymphatic fluid moving through expanded intercellular spaces. The slow waves building and releasing across the cortex. The hippocampus preparing to replay and reorganize. The emotional content of recent experience beginning gently to be metabolized. None of this requires any effort. It requires in some sense the opposite of effort. It requires the particular quality of stillness that is already present in this moment, in the weight of the body, in the slowing of thought, in the soft and increasingly distant quality of everything that seemed important a few hours ago. The universe runs most of its essential processes invisibly through components that cannot be seen or detected or directly confirmed. The brain runs most of its essential restorative processes the same way, hidden automatic, requiring only the one condition that is already being met. The night continues its slow work, and whatever needs to be understood can for now simply be allowed to settle. And somewhere in that settling in the particular stillness between the last conscious thought and whatever comes after, there is something worth noticing, not urgently, but gently. The way the invisible processes of the universe and the invisible processes of the body share a quality that has no precise name, a kind of patient depth, a labour performed without witness, a care for structure that needs no acknowledgement to continue. The night holds both of these things simultaneously without any effort at all. Part 11, and in a universe that holds more than it shows. Word count 3150. There is a kind of companionship that does not require presence. Not the presence of another person or another voice or any arrangement of matter that can be seen or touched or named. Something more ambient than that. The companionship of a world that continues while you rest. Of processes running steadily through the night without needing anything from you. Of a universe that has been holding its invisible structure for nearly 14 billion years and will continue holding it long after this particular hour has passed into morning and morning, into the long accumulation of ordinary days. This is not a comfort that needs to be believed in. It is simply what is happening. Right now, as the breath slows and the body settles more fully into whatever is beneath it, the expansion of the universe is continuing at the rate it has maintained for billions of years. Dark matter is threading through the walls of this room and through the bones of every sleeping person without acknowledging any of it. The cosmic microwave background is arriving from every direction in the sky, carrying the temperature variations of the early universe across a distance that has no comfortable analogy in human experience. None of it pauses, none of it waits, none of it requires that anyone be awake to witness it. There is something deeply restful in that if it is allowed to settle rather than being held at arm's length. Scientists suggest that one of the most striking features of the universe's invisible components is their stability. Dark matter, whatever it is made of, does not decay on any timescale relevant to cosmology. It has been present in essentially the same form since the first fraction of a second after the beginning. It did not change when the first stars formed. It did not change when those stars exploded and seeded the surrounding space with heavier elements. It did not change when some of those elements gathered themselves into planets, or when chemistry on at least one of those planets eventually produced the molecules of life, or when those molecules eventually produced something capable of noticing the night sky and wondering about its composition. The dark matter halo surrounding the Milky Way is in all probability older than every atom in every living thing on Earth. The elements in the human body, the carbon, the oxygen, the iron in the blood, were forged in stellar interiors and distributed by stellar deaths over the past 10 billion years or so. But the dark matter was already there. It had already organized itself into the large-scale structure that would eventually guide the formation of the galaxy in which those stars would form. In this sense, the invisible foundation is older than everything visible that rests upon it. There is a word in Japanese mei that refers to the meaningful pause between things, the space in music between notes that gives the notes their shape, the gap in a conversation that carries as much weight as the words on either side of it, the emptiness in a room that defines the room as much as the walls do. It is a concept that does not translate cleanly into English, partly because English tends to treat space and silence as absence, as the lack of something rather than as a presence in their own right. The 95% of the universe that remains unknown could be thought of this way, not as the part that science has failed to explain, not as a gap to be filled as quickly as possible, but as the emma of the cosmos, the meaningful space within which the visible 5% exists and has its particular character, the dark scaffolding that gives the luminous structure its shape, the silence that makes the signal audible. What we understand so far suggests that the visible universe could not be what it is without the invisible one. The galaxies would not have formed in their current distribution. The stars would not have clustered into the specific patterns they occupy. The cosmic web with its filaments and voids and the quiet architecture of everything would not have grown into its current form. The darkness is not decorative, it is structural. It is in the deepest physical sense what holds everything together. Researchers have found something interesting in the way different cultures historically related the night sky that touches on this in a sideways manner. For most of human history, before artificial lighting changed the relationship between people and darkness, the night sky was a constant and intimate presence. The Milky Way was visible on clear nights as a bright textured band across the sky, not a faint smudge visible only from remote locations, but a prominent feature of the ordinary night. People navigated by it, told time, by it organized their agricultural calendars around the movements of the stars and built mythological frameworks that gave the sky a kind of inhabited quality. The darkness between the stars was not an absence, it was part of the picture. In some indigenous Australian astronomical traditions, the constellations that matter most are not the bright patterns formed by connecting visible stars, the figures familiar from Greek and European traditions, but the dark regions between the stars. The dark constellations formed by the dust clouds and dark nebulae that block the light of the Milky Way were mapped and named and used for navigation. The emu in the sky, the crocodile, the snake. These are shapes made of darkness, outlined by light, readable only by someone who has learned to see the dark as much as the bright. It may be that this is a more accurate way of seeing than the one most people in the modern world are accustomed to. The dark is not background, it is content, it is part of the map. The circadian rhythm of the human body, the approximately 24-hour biological clock that regulates sleep and wakefulness hormone, release, body temperature, digestion, immune function, and dozens of other physiological processes is intimately calibrated to the natural cycle of light and darkness. The primary clock is located in a small region of the hypothalamus called the suprachiasmatic nucleus, containing roughly 20,000 neurons that fire in a coordinated daily rhythm. This rhythm is set and maintained by light input from the retina transmitted through a dedicated neural pathway, the retinohypothalamic tract that is distinct from the visual pathway and responds specifically to short-wavelength blue light. As daylight fades in the evening, the reduction in blue light input allows the suprachiasmatic nucleus to begin signaling the pineal gland to produce melatonin, a hormone that does not cause sleep directly, but signals to the body that night has arrived and prepares it for the transition to sleep. Body temperature begins to fall, alertness decreases, the metabolic rate slows, the digestive system quiets. The body moves gradually and without any deliberate effort into the physiological state that sleep requires. Studies indicate that this process has been conserved across hundreds of millions of years of evolution. Circadian rhythms exist in every organism that has been studied in sufficient detail in mammals, in insects, in fish, in fungi, in single-celled organisms. The molecular machinery that drives the clock, a set of interlocking feedback loops involving proteins called clock, BML1, period, and cryptochrome is so ancient and so conserved that versions of it are recognizable across kingdoms of life that diverged from a common ancestor more than 1 billion years ago. The body's relationship to the rhythm of light and darkness is not a habit. It is not a preference. It is among the oldest continuous inheritances of being alive. There is a particular quality to the melatonin-mediated transition into sleep that is worth noticing not analytically but experientially. The mind, as the melatonin signal builds, does not shut off. It loosens. The grip that waking cognition maintains over the contents of awareness, the sequential logic, the forward planning, the evaluation, and categorization of experience becomes less insistent. Thoughts begin to arrive and depart without the usual sense of obligation to follow them. The boundary between internal experience and the fading awareness of external environment becomes permeable. Images arise without obvious cause. Connections form between unrelated things. The ordinary editorial control of consciousness relaxes, and something less organized and in some ways more interesting begins to occupy the space. This transitional state, the hypnagogic zone as sleep researchers sometimes call it, is not sleep, but it is not wakefulness either. It is its own specific neurological condition, with its own patterns of brain activity, its own peculiar phenomenology, its own relationship to memory and creativity, and the processing of unresolved material. Many people who work with problems that require creative or non-linear thinking report that this state and the moments immediately upon waking are among the most productive. The loosening of conventional associative constraints allows combinations and connections that the focused waking mind would have dismissed or simply never considered. The brain tends toward a kind of generosity in this state. A willingness to hold contradictory ideas simultaneously to allow images to transform into other images without demanding consistency to follow the internal logic of a developing thought, without measuring it against what is already known. Scientists are still exploring the full functional significance of this transitional state. What is known is that it's not a failure of wakefulness. It is not the brain losing coherence on its way to sleep. It is a specific and organized condition with its own architecture different from both wakefulness and sleep, valuable in its own right and almost entirely invisible from the outside. The person lying still in the dark, thoughts beginning to drift and soften and connect in new ways, is not simply waiting for sleep. They are in something that the body produces deliberately in the right conditions as part of the long and layered process of rest. It may be that the universe works in something like the same way that what appears from the outside to be mostly darkness, and absence is from within a more complete understanding, a specific and organized condition. Not empty, not waiting, not a failure to be luminous, but something with its own architecture and its own functional role in the larger system of which the visible 5% is only the most recently arrived part. Evidence suggests that the human experience of the night has changed more in the past century than in any previous period of human history. Artificial lighting has extended the waking day to a length that most human physiology was not designed for. Light-emitting screens emit blue spectrum light that suppresses melatonin production and delays the circadian signal that prepares the body for sleep. The darkness that was for most of human history the natural condition of the nighttime hours is now for many people in the industrialized world an experience that requires deliberate effort to create. What researchers have found is that this change has consequences for sleep quality, for circadian alignment, for the prevalence of the metabolic and psychological conditions associated with disrupted sleep rhythms. The body still carries the ancient machinery. The suprachiasmatic nucleus still waits for the blue light signal to fade. The melatonin pathway is still ready to begin, but it needs the darkness to receive the cue that it was designed to receive. The darkness is not merely the absence of light. It is information, a signal, the message that the world sends to the body every night in the language the body has always known, saying this is the time, this is the condition, you can let go now. And letting go, it turns out, is not a passive thing. It is something the body does actively with considerable biochemical precision through systems that have been refined across geological time to perform exactly this function at exactly this hour. The heart rate has already slowed. The muscles have already released most of their tension. The breath has already lengthened into the slower, more even rhythm of body, no longer maintaining the alert readiness of waking. The glymphatic system has already begun its gentle circulation through the brain's expanded spaces. The slow waves of deep sleep or their precursors are already beginning to organize in the neural tissue. All of this is happening without any instruction, without any effort, without any awareness of happening at all. Just as the dark matter is holding the galaxy in its shape without instruction or effort or any awareness of anything. Just as the dark energy is pressing space gently outward in all directions, steadily without pause or deliberation. Just as the ancient light of the cosmic microwave background is arriving from every direction in the sky, carrying its information from the earliest moments of time without knowing it is carrying anything. The universe continues its invisible work, the body continues its invisible work. And the particular awareness that has been following this long and quiet thread of thought through the hours of this night is perhaps beginning to find the edge of where thought ends and something quieter begins. There is nothing left to understand before sleeping. There was never anything left to understand. The understanding was always beside the point, a gentle companion to the experience, not a condition of it. The room is as it was. The dark is as it has always been, older than the earth, as full of invisible motion as the cosmos it is part of. And whatever awareness remains in this moment, soft and unhurried, and no longer particularly interested in keeping its own edges clear, is already drifting towards something that needs no description, because it has no outside, no observer, no distance from itself. The night has further still to go, and it goes quietly on its own. The universe does not know that it is being observed. This is not a poetic statement. It is in the most literal sense simply true. The dark matter flowing through this room has no awareness of the instruments built to detect it. The ancient photons of the cosmic microwave background carry their information across billions of light years without any intention of delivering it. Dark energy presses space outward through the night without knowing that anyone has noticed or named it or spent decades trying to understand what it is. The universe simply continues, patient, vast, mostly invisible, largely unknown. And there is something about arriving at this understanding not dramatically, not as a revelation, but slowly through the accumulated weight of a long night's worth of quiet attention, that feels like a particular kind of arriving. Not at an answer, at a resting place. In the year 1995, the Hubble Space Telescope was pointed at a region of the sky near the handle of the Big Dipper that appeared to every available instrument to be completely empty. No known stars, no catalogued galaxies, just a small dark patch of sky, roughly 1/30th the apparent diameter of the full moon, selected precisely because nothing was there. The telescope held its gaze on that emptiness for 10 consecutive days, 150 orbits. The photons arriving from that direction accumulated on the detector faint signal by faint signal building slowly into an image that no one had seen before, and that no one who has seen it since has found easy to forget. When the image was processed and released, it showed approximately 3,000 galaxies in a patch of sky that had appeared completely empty, each one of those galaxies containing hundreds of billions of stars, each one of them at distances ranging from hundreds of millions to more than 12 billion light years. Each one of them surrounded by an invisible halo of dark matter, its structure shaped by the acoustic oscillations of the early universe, its position in space reflecting the underlying geometry of a cosmic web that no photograph can directly show. In a patch of sky that had appeared completely empty, researchers later repeated the observation with more sensitive instruments, the Hubble Ultra Deep Field, then the Hubble Extreme Deep Field, pushing further into the dark, finding more galaxies each time, until the count from a single small region of apparently empty sky exceeded 10,000, then 15,000, each image a window into deep time as much as deep space, the most distant objects in each image, visible as they were when the universe was only a few 100 million years old. The universe is not sparse, it is not empty in any direction that an instrument has yet been patient enough to examine. It is dense with structure, dense with history, dense with light that has been travelling for longer than the Earth has existed, all of it flowing continuously through the dark in every direction, whether or not anyone is watching. There is a question that astronomers sometimes sit with not as a technical problem, but as a kind of contemplative exercise which concerns the light that will never arrive. Because the universe is expanding and because that expansion is accelerating, there are galaxies beyond a certain distance whose light travelling toward us at the speed of light is nevertheless being carried away by the expansion of space, faster than it can close the distance. The light leaves, it travels, but the space it is crossing grows faster than it can cross it. This means there is a boundary, a cosmological horizon beyond which no signal from us can ever reach any observer, and beyond which no signal will ever reach us. The galaxies beyond that horizon are not merely far away, they are in the most precise physical sense unreachable. Whatever happens, there will never be known here. Whatever we do here will never be known there. Scientists suggest the existence of this horizon does not trouble the galaxies on the other side of it. They continue forming stars, evolving, moving through their own local portion of the cosmos, entirely unaware that they are invisible to us as we are to them. The universe is full of regions that have no causal contact with one another and never will. And within each of those regions, the same invisible components are present. The same dark matter, the same dark energy, the same background of ancient light, the same 95% that remains unknown. It is not only our universe that contains more than it shows, it is the whole of everything, everywhere, in every causally disconnected region of a cosmos whose full extent no instrument will ever map. The word universe comes from the Latin universus, meaning turned into one or combined into a whole. It was the word chosen to describe everything, the total, the complete set of what exists. But what cosmology has slowly revealed is that even the universe in the most technical sense, the observable portion, the roughly 93 billion light years of space accessible in principle to human instruments, contains within it a majority that is neither observed nor observable in any direct way. The whole contains a hidden interior that may be larger and more significant than the surface visible to all available eyes. It may be that this is simply the nature of wholes, that every sufficiently complex system contains more than can be seen from any particular vantage point within it, that the visible is always a fraction, that depth always exceeds surface in every direction in every domain. The ocean holds more than its surface shows, the forest holds more than its visible canopy, the sleeping brain holds more than the stillness of the body suggests. The universe holds more than 14 billion years of light as yet revealed. This is not a reason for anxiety. It is, if anything, the opposite. The world is deeper than it appears. The night is fuller than it seems. Whatever is present in this moment extends in every direction further than perception can follow. The breath slows now, naturally, without instruction. The body has known how to do this for a long time. Somewhere above the sky holds its particular depth. Stars sending light outward in every direction. Ancient photons completing journeys measured in billions of years. Dark matter flowing through the room without acknowledgement. Space pressing gently, continuously in all directions at once. None of it requiring anything, none of it waiting. The glymphatic fluid moves through quiet channels. Slow waves cross the cortex. Somewhere in the Black Hills a detector listens. Somewhere above the atmosphere a telescope turns. The cosmic web holds its shape. The ancient light continues. The expansion continues, unhurried, even, vast. You do not need to hold any of this. It will continue without being held. The dark matter will be there when the questions return. The ancient light will still be arriving. The universe has been carrying its invisible weight for nearly 14 billion years. It does not need your attention to continue. The breath is slower now. The edges of things softer. Somewhere very far away in a direction no instrument has yet named, light is travelling through the dark. It has been travelling for a very long time. It is in no hurry. It will continue long after this night has ended. Long after every question asked tonight has been set gently down. The dark is not empty. It is full of what cannot be seen. And that is enough. More than enough. The night holds everything, and you are already part of it, already held, already still. The light continues, somewhere quietly as it always has.